There we go. Yeah, so question 10, what is the maximum number of electrons that can have n equals 4 in an atom? Well, when we have n equals 4, when n equals 4, we have, right, 4s, we have 4p, we have 4d, and we have 4f. At the s orbital, we only ever have one s orbital, and we'll have 2 electrons in each orbital. So I can have 2 electrons at 4s, got 3 p orbitals, 2 electrons each. So that's 6 electrons I can hold there. 5 d orbitals, 2 electrons each. So that's 10 electrons there. 7 f orbitals, 2 electrons there. So that's 14 electrons total. Add those all up, I get 10, 20, 30, 32 total electrons can have n equals 4 for their quantum level at a maximum, right? All we have to do is figure out I have s, p, d, and f, and then how many of those electrons do I have at each of those orbitals for question 10. All right, for question 11, what set of quantum numbers cannot exist, right? So our first thing is we start with n, right? N, the next thing is L, and L can equal 0 to n minus 1. And then the next component we have is ML. Well, n can be, 1, 2, 3, 4 through infinity. ML can be negative L to positive L. So, okay, I've got n equals 3. L cannot be greater or equal to n. So our first one works out because when L is 2, yeah, n is 3, L can be 2. When n is 1, L can be, when n is 2, L can be 1, sure. N is 4, L is 3, that's fine. N is 4, L is 2, that's also fine. I think the other one doesn't show up, but we're okay. All right, now based on my value of L, right, based on my value of L, ML can be plus to minus L. So right here, we run into a problem because when L is 2, I cannot have a value of negative 3, right? When L is 2, we're talking about our d orbitals. We only have 5 d orbitals. This is telling us, this is trying to tell us we have 7 d orbitals. We don't. So that is an orbital that does not exist. ML can be 0, that works. ML at plus 2, that works. ML at plus 1, that works. But yeah, choice A does not exist because that value of ML is an orbital that does not exist in the d orbitals, basically, for question 11. And 13 is next. All right, so which one of these does not obey Hund's rule, right? Hund's rule just says we're trying to maximize my spin-aligned electrons by making sure that each orbital has 1 electron before I pair up. And if I look at all of these, right, 1 electron, they all have 1 electron. Yes, they have a pair, but this orbital has an electron, paired, but this orbital has an electron. So choice E down here, we violated Hund's rule because rather than put those 2 electrons in different orbitals, they're in the same orbital and they're paired. So that's a violation of Hund's rule. We should have one of these electrons in the next orbital. Right, so the Aufbau principle, basically it's what we're following when we're making our electron configurations, when we're going in the periodic table and we're placing electrons in each orbital. We want to go and make the lowest energy configuration. So you always want to fill the lowest energy orbitals first. So what we're looking for is basically one where we skip orbitals. So 1s2, 2s2, 2p6, 3s2, that's fine. 1s, 2s, 2p, 3s, 3p, 4s, that's fine. 1s, 2s, 2p, 3s, 4p. We basically skipped the 3p orbital, we skipped the 4s orbital, right? So that's not a Bang-Hun's rule. We've skipped orbitals that are lower in energy and we jumped right to 4p. We can't do that. Everything else is fine because it's, 1s, 2s, 2p, 3s, 3p, 4s, 3d, that's fine. And E is fine as well, right? So we want to have our lowest energy configuration. We want to do that by filling the lowest energy orbitals first. Question 14, we want to find technetium on the periodic table. All right, my handy little clip art here, my periodic table. So technetium, atomic number 43. And so we're right here. So I'm going to drag that back over. Right, so the condensed configuration of technetium, I would go back to krypton, sorry, don't know why I circled argon. Go back to krypton. So krypton would be my nearest complete noble gas to get to technetium. So there's krypton. Right here are s orbitals. So 5s2 takes me to strontium, and then remember 4d is next. So 4d, 1, 2, 3, 4, and 5 take me to technetium. So now let's answer those questions, right? The core electrons, that's the noble gas core electrons, right? So Bree, who asked this question earlier, how do we find our core electrons, right? Our core electrons are our complete noble gas configuration electrons. So for technetium, we've gone through the noble gas of krypton. We have the electron configuration of krypton. So my core electrons are krypton. The unpaired electrons are in the, okay, so we need the orbital diagram as well. So the orbital diagram is going to look like this. We only need it for the valence electrons, right? Valence electrons are everything that's beyond our noble gas configuration electrons. So 5s and 4d, so 5s2, 1, 2, and then 4d5, 1, 2, 3, 4, and 5, following Hund's rule. So now we can answer the rest of those questions. There are 5 unpaired electrons, right, in the d orbitals, and those electrons happen to be in the 4d orbitals. And that finishes out question 14. So any questions on that?